Hello again, I'm back with another review of my Rohde Schwarz RTB2004 300MHz oscilloscope. Also in this review I'm going to be comparing it, or looking at the screen resolution in comparison to my Keysight 3014T, which is actually a 100MHz scope. I don't have the option for the 200 megs on that, but it's optioned at 100 megs at the moment. The signal showing on the screen, on both screens, is being generated from the Keysight. It's one of their demo signals, which is a square wave with sinusoidal noise running on top of it. And I've tried to adjust the time base and the vertical sensitivity on both screens to get a very similar amount of detail in terms of full screen coverage, showing the same amount of the wave, and then I've actually run-stopped both of them. These screens were produced using high resolution mode on both scopes, and I think 5 megasamples for the memory depth on the RTB2004. Obviously the memory depth on the Keysight is not adjustable, the scope just uses the maximum amount which it can do. But interestingly enough, and I'm going to zoom in a moment and look at these so you can see them clearly on the screen, the actual detail, because of the 10-bit resolution ADC on the RTB2004 as opposed to the 8-bit, which is what the Keysight has and most scopes have, I actually think and also there's a high resolution screen pixels on the RTB2004. I actually think the screen waveform is far more detailed on the RTB2004 than on the 3014T. But what I'll do is now I'm going to zoom in and have a look at them individually so you can see the details on that. This is now showing the waveform on the Keysight 3014T. Obviously that's with it run stopped, and that was with the acquisition using high resolution mode. The time base has been adjusted, as I said before, so that you get the same basic waveform showing in both screens, but obviously this screen is smaller in terms of physical size and also in the number of cells going across than the RTB2004, but I positioned it so that you get hopefully pretty much exactly the same waveform area showing. If you just look at the actual waveform there, you can see that it just looks a little bit blocky, although it's not a bad representation of the noise on the waveform. To me it just looks a little bit blocky. Now when we compare it to the 2004, which I'm just about to show you now, that's the same waveform run stopped in high resolution mode on the RTB2004, and in actual fact with the 10-bit ADC there is definitely more steps and more detail that's been shown in the waveform. And it's quite common that I've noticed when I'm comparing these two scopes that definitely the screen resolution on the RTB2004 is often superior to the Keysight, and very much superior also to my Rigol DS2000, although the 2000 Rigol is probably very similar to the Keysight. It's just that this physical screen on the RTB is one, higher resolution in terms of the number of pixels, and secondly the 10-bit ADC just picks up more steps when you're looking at waveforms. Obviously on some waveforms that doesn't particularly matter if you're looking at a large time base where you're not looking closely at the waveform, that may not be so important. But when you're actually looking at noise signals, or you're looking at something where you want to see the finite detail, I actually think that the RTB2004, the screen is definitely superior, far superior in regard to the Keysight 3014T and any of the 3000 series or 2000 series, and probably the same with the Rigol. I only had the 2000 Rigol, but I would imagine it's probably the same with the 4000 Rigol, and probably the same with the, I think it's the 1000 series. It's just the 10-bit ADC does make a difference. Whether that would make a big difference in daily use, that's a different matter, but certainly it does appear to look nicer. I'm now looking at a signal that I'm again generating from the Keysight. It's one of their demonstration signals that's included on the scope, which is a sine wave with a glitch on it, which actually can be seen occurring on the top of the waveform occasionally. Now at the moment I'm running it in sample mode, so it's only picking up those glitches occasionally. If I go to peak detect mode by clicking on sample and clicking on peak detect, I'm now, get rid of the menu, I'm now seeing that glitch all the time. So you've now got the vertical line glitch showing all the time because it's in peak detect mode, and that acquisition mode will look at the peaks on any of the signal and not average them out, so it's including those. If I then go down just so we can see what it looks like on the other modes, high resolution, it actually makes the waveform thinner because I think it's doing averaging, which is standard on most scopes, internal averaging. If I go to average mode, I'm actually on 2 averages there. I can change the number of averages, so if I click on the average there, go to menu, click on my average there. Now again, I can either bring up by double clicking, so I did it 3 clicks, I can enter my averages, so I can put 24 averages, enter, click on that, so I'm now, that'll go away in a minute, got my triggers, that'll go away now. That's now showing the signal running with average mode with 24 averages. Although this is a clean signal, so it doesn't actually really need average mode. You can run any number of averages on this, running, I believe when I click on that, it tells you anything from 2 up to, I think it's 1,000,000 averages, but it does slow the scope down considerably. So if you've got a signal that's varying, like most scopes, and even on the Keysight, and particularly on my Rigol, I'm not sure that I think the averaging is probably done in software and not on the actual FPGA hardware, so consequently it does actually slow the scope down. I'm using also on this 5 megasamples as a record length, so we can actually change the record length on this and change the length from 10 kilosamples, 20 kilosamples, 50, 100, 200, 500, 1 megasample, 2, 5, 10 and 20. Obviously the Keysight I think is only 4 megasamples maximum. This has got a much larger memory, and this comes in very handy when you're doing serial decoding. Let's put it back for the moment because I don't really need anything more than 2 megasamples for this. You can put it into automatic mode actually. Let's put it into automatic mode, and that will choose its own record length. Now if we take that and go from average mode, now we can look at envelope mode. Envelope mode gives you basically an outside edge to the waveform, and you can see the waveform building up, so it stores all the acquisitions. It's basically the persistence mode is showing all the data there over a period of time, so you're seeing that it's getting much thicker trace. This also because of persistence is showing up all the time now, whereas in other modes I had persistence turned off, but we can go back and turn that on again in a minute. The last one is envelope with peak detect. Let me just put that on, I didn't click on it. Envelope with peak detect. So that's doing another envelope mode to get persistence and showing the whole waveform with persistence in an envelope manner, but it's also showing a peak detect, so we're getting the same as the peak detect mode, so we're getting this showing up, the glitch showing up very neatly now. We come back out of that and go back to sample mode. We're back to there, and you can see that with the waveform update rate, which I think is up to about 50,000 waveform updates per second, this is showing up periodically. The glitch is showing up periodically on this scope, but of course if you wanted that to show up all the time, you would just select the peak detect mode, which is more suitable for this particular waveform because of that glitch, and that's picking it up full time. So that's a sine wave. I'm going to show another wave just so that you're getting a variety of different waveforms, and you can see the sort of quality of this screen, which is quite something when you're used to, say, the Rigol or even the Keysight, which is still a very expensive scope. I just find this screen is so much better. This is another waveform example waveform from the Keysight, which is a 500 kilohertz digital pulse with a ringing on it. So you can see the ringing on the top. If I zoom in to that, I can then move my signal across with my finger. When you actually move, it's difficult to see, the actual cross shows that we're moving left to right because the arrow under my finger, which you can't see, is diagonal. If I'm doing that way, the arrow goes vertical. It's just difficult to see. I think you probably can see it. Yeah, that's now a vertical arrow. If I click and then move sideways, you can see the arrow is going left to right horizontally to show that I'm moving it left to right. I can also change the colour of the waveform. So if I go into my channel menu and I go down to the bottom, sorry, I've gone the wrong way, waveform colour, it's in default, which is yellow for the channel 1. I can go rainbow, fire, which looks the same at the moment, or temperature, which is white. And I believe these actually, temperature changes colour dependent upon how frequent the signal is, but obviously on this signal their frequency is the same. There's no glitches that are infrequent, but the colour will change. If we go back and put it on default, it goes back to that. I can also, in this menu, which is my channel menu, I've got my AC and DC coupling, my grounding if I want to ground it. I've also got my, sorry, I'm changing the colour again, onto the wrong one. I've also got my bandwidth limit, so if I want to go on to 20 megahertz bandwidth limit as opposed to the full, and you can see that's the full, so we've got a higher waveform there. When I click on 20, we've gone down to 20, showing that the signal has been made smaller by limiting the bandwidth there to 20 megahertz. You've got vertical scale here, so obviously I can alter my vertical scale here. I'm at 500 millivolts. If I want to put in 650 millivolts, I can enter that there, and you can see it's gone smaller because each cell now has a larger value. If I want to go the other way, I can make it cover more of the screen by, say, going 300 millivolts or 300 M, and now that's smaller. Now I can then adjust my position by altering my vertical, either using the controls or just my finger on the screen, and I can also move left and right, obviously. If I zoom out, we'll get back to all the signal again, and but again that shows the clarity. It is, to my mind, the signal is just smoother than, say, on my Keysight, which is one of the reasons that I particularly like this scope. Okay, for my final quick demo, and it's just a brief one, I'm showing now an I2C signal. You'll have to excuse the glare. I'm getting a slight bit of reflection off the Keysight screen, which, funny enough, I don't seem to be getting off the RTB2004, probably because the screen protector being matte, it's slightly less prone with the lights I'm using. But I'm using the demo signal that's built into the Keysight I2C. And I'm sending the same signal, which I'm going to demonstrate in a minute, on the RTB2004. So I've got this to trigger on a 29 read with acknowledge, with the first data bit being FF in hexadecimal with an acknowledge. If you then look, you'll see that the second bit of data in that same stream, which is over here, so 29 read, acknowledge, data's FF, acknowledge, that's an 80 and a C0 with an acknowledge, and the bit's changing. In their demonstration you can see the bit actually moving and changing pretty quickly. You've then got the next bit in the stream of data coming through, which is 71 write, acknowledge, 00 acknowledge, then 70 write, acknowledged, 04A acknowledged. If I go to the lister mode on the Keysight, it gives me the data in a table form, which is similar to the bus table on the RTB2004, and you can get this data out and save it to the USB, which you can do on both scopes. But you can see that the top one, where I'm triggering on 29 read FF, you can see that that's 80 or CO, and it's changing fairly quickly between the two, because the data that's being sent is continually changing, probably at sort of 8 or 10 times a second, so it's sort of just glittering between one and the other all the time. So if I then come out of that, you can see the top signal being the clock signal and the bottom signal being the data. on that I2C signal. What I'm now going to do is change my position and show you the screen close up with the same data exactly being captured on the RTB2004, and that's being fed from the same inputs, RTB2004. At the top here we've got the serial clock, and then this is the serial data in green. Underneath it we've got the protocol decode, which again was on the bottom on the Keysight, but you can't move it on the Keysight. On this scope, because I'm selected on the protocol, I can move the protocol either physically on the screen with the mouse or with the position knobs, which are indented. What I can also do, which I can't do on the Keysight, is to change the width of that, so it's quite sophisticated, the display. So I'm making that narrower, making that larger, and that's quite useful, particularly when you're showing, and I will do another video where I'm actually showing this in binary, where you've got longer 8 bits of binary data. You can actually make this longer, and then you have 3 lines of binary data, or any data that you're displaying for that matter can be shown across more lines. We're getting the same data. If I use the pointer, we've got 29 over here. We've got the data, which is FF hex, the H being hex. We've got this data, which is the one that's changing, which again, because this is decoding, and the RTB, I'm sure of this, decodes on the FPGA and not in serial. If I was doing this on my Rigol, it would be very, very slow. It would work, but it would be very slow because it's doing it in software. Again, the RTB2004 is doing it in hardware, in the FPGA, which I think is an Altera FPGA they use, and you can see the bit changing up here, but the decode is also changing here at the same rate like it was on the Keysight. So you can see it's changing from, I think it's 80 to C0 hex. These are stationary because it's 71 hex right, data 00 hex right, 70 hex, and then the data 04 hex. I've got the same sort of amount of data. What is also nice on this screen is the bit display, which you can turn off. So above the decode data you've actually got the bits, which are the same representation as the green. So you can actually see this green one that's changing here, which is the bit data that's changing from C0 to 80, is actually changing there, and you can see that bit where I'm circling around there flashing, and that small bit representation is changing. As I did on the Keysight, I can also bring up a table, a bus table, so I've already got that set up. So if I pull my menu up here, my split screen, I've now got my bus table here. I've got measure here actually. If I put the measure off, it'd be easier. I've got my bus table here now, and I've got my frame number, my start time, and you can either have start time, or I think you can have time between actual frames depending on what you want to set it at. And we've got here 29 write, ID length 1, so it's 1 bit of data, 04, and it's acknowledged, so it's okay. We've then got read 29, 2 bits of data, which is FF, and then the second bit, which we saw, which is the changing one, which you can see is going from 80 to C0, and that bit is continuously changing. Not quite as fast as on the Keysight in the table, funnily enough, faster on the screen, but it's still changing fairly quickly. In actual fact, it's easier to read on this than it is actually on the Keysight, where it's flashing so quickly. So they may have purposely have slowed this down, because you can see it's flashing much quicker here, but they may well have done in the software, the display software, because this is done in hardware, the decode, but the display software has probably been slowed down so that you can actually see that data and easier to read, because I can read that as FF, and then it's 80 C0, 80 C0, which is much easier to read than on the Keysight, which may be more accurate to show it fast, but obviously much more difficult to read, and you probably have to run stop it to read it. And OK there, because it's probably acknowledged. Then we've got the next one, which is write 70, 1 data length, and it's 04. And then the final one here we've got on the screen, which is write address 64, which I don't think I can quite see on the screen, but it's still showing in the table, 1 bit of data and DA. And of course, being that this is so flexible in its design, if you want to make this table bigger, so if you had this smaller, so if we turn the time base and make this smaller, you can see now that I've got more data at the top of the screen. Difficult to read, but it's populated my table here. So if you were reading some data from a microcontroller and you wanted to read, say, 6 or 7 bits of data, maybe you were asking an accelerometer, say for instance in I2C, you were asking it for some data, so you sent it its access number and you sent it this particular code in hexadecimal, and then it responded. You'd be able to see all your data here. This table can also be saved, so you click on this here and you can go again using the USB on the front and you can save it. I don't have a USB in, so it's not highlighting the save, but it would allow me to save this as a table that I could then take out and read, I think in probably Excel. I don't know if it's a CSV file, but it's probably saved as a CSV file, but I will have a look at that in due course. This is just a very quick brief look at how this worked, just to give an idea of how the decodes work on both scopes. But certainly the decode on this RTB is very flexible. One, in that it's very quick, because I believe it's done in hardware, and I did ask somebody at Keysight, sorry, did ask somebody, maybe I might point and ask them at Keysight, sorry, I did ask them at Rohde Schwarz whether this was done in hardware for the decoding, and they confirmed that it was, not software, because one of the reasons that I went away from my Rigol was that I was doing a lot of decode work, not so much I2C but more CAN bus decode work for cars, and I couldn't, for a project I was working on, I couldn't just find, I found that my Rigol was just too slow for it. I do like the Rigol in certain ways, in actual fact in certain ways with its measuring and some of its menus. I think it's a great scope, and it's one that I've had the longest, but just for decoding, probably my favourite is probably the RTB2004, and then very close behind is the Keysight. But I do particularly like the flexibility in the display, in that you can move your protocol decode, you can scale your protocol decode both vertically, which you can't do at all on the Keysight, it's fixed vertical height, and you can also scale it horizontally, but with the time base, which of course you can do on the Keysight as well. What I was saying before about the bit pattern is here, and you can see it now. The bit pattern is here, and you can actually see the bits across the top, and those will mimic the bits on the data here. So in actual fact, sorry, the top one is the clock there, and then underneath the bit pattern is the data. So if I bring that up, I can actually see that the top one there is matching my clock. So if I look at this top bit pattern there, the right one, right at the top of this one in sort of burgundy colour there, I think it's burgundy. If I push that up to the yellow, you'll see that's mimicking that. If I bring that down and then I look underneath, probably easier here with this rogue bit here, there's one single bit here, that's that bit there. So if I bring that up, you'll see that that matches with that. Now I can switch that off. If I go to protocol, I'm pretty sure it's in protocol, I can go to display setup, yeah, bits. So I'm showing this as hexadecimal. I can actually change that to binary, so now my data comes out as binary. Go back to hexa, close that menu, easier to do protocol, display setup, I'll go back to hexadecimal. Now if I switch my bits off here, you can see instantly that now the decode is clean, there's no bits at the top. I just happen to prefer it with the bits on. Sometimes it may be easier actually to see it without the bits, but the advantage with the bits showing is that you can of course switch off your channels. You can switch off your display of your analog channels if you're reading it in on analog. Of course you could read this in using the digital logic channels, but if I switch off, I'm pretty certain I can switch off my analog channels, 1, 2, and I've still got my Decode running, and you can see my Decode is all there and it's still decoding. So because I've set it up, it's still decoding in the background, but I don't have to have the display on. So if I wanted to have some other signal, say another analog signal that was something else that I had a problem with, but I wanted to correlate it with data coming in on this bus, on say an I2C bus, I could say have channels 3 and 4 showing, which might be analog signal, which might be something related to but not a digital signal within the same system. So from that point of view, it's quite useful to be able to switch off the signals here, the 1 and 2 signals, channels 1 and 2, to make space on the screen if, for instance, you were reading in data, say, from a accelerometer, but also then something else was happening at the same time, that you might be, because of a movement on an accelerometer, you might be, for instance, actioning something else with a digital signal but not on the I2C bus. You might well want to use channels 3 and 4 and might want to see them on the scope. So it's quite useful to be able to switch the channels off but still have your serial decode data at the bottom showing. This has a number of decodes on it, so when you go to protocol decode, you've got different types of decode that you can do on this. So at the moment this is set up as we've been doing for an I2C, but you've got on it SPI, you've got CAN, I think you've got LIN. There's a whole variety of different types of decode options that you can have, which are licenses like most scopes, but this scope has the licenses for a whole variety. In actual fact, there is also a demo on this scope of those. So I think I've shown this before in the first video. When you go to protocol, and this is on the app selection, you've got SPI 3-wire, SPI 2-wire, I2C, which is what we're just showing at the moment, but obviously this is generated from within this scope. I was using a signal from the Keysight just to show it receiving data. UART, CAN and LIN, and what I would say is that I've also, and I will show it in another video, I've been using another device to bring in signals for testing purposes, which is National Instruments, sorry, because the name just escaped me for a moment. It's a National Instruments My Rio, which is a unit that's an FPGA development system that's driven by LabVIEW, and I've been generating signals up to 50 megahertz digital switching signals, plus I've also been sending out signals from it in terms of CAN bus signals from it, which it can generate. And what I was doing, I was using one decode for the CAN, and I was also using the digital lines, using the pods down here at 50 megahertz, and it was still, the scope was quite happy to do 2 protocol decodes at the same time without slowing down, and I didn't have any problems. So everything I've thrown at this scope in terms of serial decode, I've not had a problem with. It just seems to decode it, much like my Keysight, which you can throw anything at and it decodes it perfectly. The decodes on this, I think, are very good, but I think that's probably from the fact that a lot of the operating system from this comes from the Rohde Schwarz higher level scopes, which I think are their RTO and their RTM versions, which have had serial decodes for a number of years on them, and it's basically a very well action software or firmware, or actually written in FPGA, so it's hardware actually, but basically it's been researched very well, and I find that it just works without a problem. Whereas again, not to slate my Rigol, I found on my Rigol, one, it's just slow, and secondly I've also found that sometimes when I was trying to decode something from an accelerometer on I2C, my Rigol just would not read it, whereas when I put it into either this RTB2004 or before that the 3014T, the Keysight, I just had no problems with it. It just decoded it instantly. There's a lot of other features on this decode which I will go into, but that's a separate video. I'll probably do a video on UART and probably SPI. The decodes are really very powerful, and I could do a whole probably hour or 2 hour video just on the decodes, but I will look at showing that using the My Rio so that you can see it bringing in signals again, and I'll probably show it actually decoding, say, an I2C and a UART at the same time, because it, as I said, it just doesn't slow down, which on some scopes, even on some of the Tektronix ones, sometimes when you switch on other parts of the system it slows it down, whereas I just haven't found it particularly on this scope at all. Certainly on my Keysight it doesn't slow down at all, but that's known for that. But certainly on this RTB I've really been pleased with it. It just doesn't slow down. It just seems to work whatever you throw at it, basically. The other thing, just to finish up, because obviously this video is getting a little bit long again, what I would also say on this scope is that on this latest firmware I've not had any course to reboot the scope. In actual fact, with any of the firmwares, I've been using the scope now for almost 6 months, and basically I've found that not once have I had to reboot it, which again, dare I say it, with my Rigol I've definitely had to reboot. Not so much recently with the latest firmwares, but in the early days Rigol would often, you select something and it would often crash. I've not had this system crash once. Neither have I had a problem with any of the touching of the screen and signals coming in and being affected on the input channels, because there was a video which EV Blog did, which Dave suggested that when you have a signal on from another channel and you touch the top of the screen, you tap the screen. Let me just switch off these channels and let me just switch up the sensitivity on this too. Right, that's at 1 millivolt. He was suggesting that when you do that, when you tap the screen, you are getting so much noise. I'm not triggering on that because I'd have to switch that trigger on. I'd have to switch the decode off. But basically I haven't had a problem with that. Neither have I had a problem with the screen, because he was demoing that when you were poking at the screen you were getting signals being affected on your channels, but the channels were open actually. But I've not had that problem at all, either when they're open, but of course you wouldn't be feeding in a signal, or when I've actually got a probe plugged in. So I've got 2 probes at the moment plugged in, but I've not found any problems with signals. So that if I switch on that, let's say I switch that one off, bring this one down a bit, let's just say I turn the amplification up on it a bit, bring that down on the screen, you know, I'm tapping the screen, and quite frankly I don't think most people would normally tap their expensive scope so hard. I certainly wouldn't continue to do that, do it for a video once or twice, but that's it. The same thing with the screen. I don't hit the screen, it's a touch screen like a tablet. You just touch the screen, hence touch screen. So I've not found any problems with it crashing, or with any problems with this suggestion that the channels were, the way they were mounted, was sensitive to vibration. Certainly where I've got it sitting in my lab, I've not had any problems on that. As I've said, I've been delighted with the scope so far. Okay, I think I'll leave it at that for the video today, and then what I will do is the next video I'll probably look either at serial decodes, or no, probably actually we'll look a bit further at serial decodes, and then after that I'll consider what I then do for the next stage. But I hope you've enjoyed that video. I hope also the audio wasn't too bad on this video. Somebody had suggested there was a hissing noise. I was going to get an extension cable, which I did for my microphone, but I actually found I got more noise by using the extension cable. I think the hissing noise is actually coming from the lights, my lights that I'm using in my lab to get enough light for the video. I think the fans in that are making the hissing noise, so I will try and work out a better way of mounting the mic further away from the lights, but I'm still working on that. But I hope the audio for this particular video hasn't been too bad. Thanks for watching, and I will return probably in the next few days to produce another video. Thanks indeed. Bye.